things that this recombination does is it's going to create new multi-locus genotypes very, very quickly. So in this chart that we're seeing here, we've got time, so we're going through multiple generations on the x-axis, and we've got one population that's asexual and one population that is sexually reproducing. We start out in both populations with all of the individuals having the multi-locus genotype of little a, little b. Over time, a mutation occurs that converts little a to big A. And big A has a selective advantage. So big A is going to increase in frequency in the population. Subsequently, in another generation, there's another mutation from little b to big B. And big B also has a selective advantage. And let's suppose that these effects of big A and big B are additive, so that big A, when it's combined with big B, has a greater advantage than either big A or big B on its own. So what has to happen in the sexually reproducing population to bring this big A and big B allele together? So notice that this big B mutation occurred in an individual that had the little a rather than the big A allele. So automatically, as soon as that mutation occurs, that population is in linkage disequilibrium for these two loci, because the big A, big B haplotype does not exist in the population at this point. But as soon as sexual reproduction and recombination creates that big A, big B haplotype, now you've got these big A, big B individuals in the population. They're going to increase in frequency very rapidly until they very quickly take over the whole population, increasing the average fitness of the whole population. So let's think about the same scenario in the asexually reproducing population. So here we've got the mutation that changes little a to big A. They have an advantage, so it's going to increase in frequency. So what has to happen in this case to bring the big A and big B alleles together in the same individual? Basically, you have to wait until there's another mutation that happens to be on this big A allele, because they're not going to recombine to bring big A and big B together. There's going to have to be another mutation that changes little b to big B that occurs in an individual that already has the big A allele. This change over time to become fixed for big A and big B together is going to take a lot longer in our asexually reproducing population. So we have several different kinds of explanations for the benefit of sexual reproduction, and they all include some explanation of the benefit of segregation of alleles, genetic recombination, and reduction of linkage disequilibrium into those explanations. So let's first look at a model system that's going to help us to examine these two different kinds, categories of explanations for the benefit of sex. So one of them is a mutation and drift model, and the other one involves selection in a changing environment. And our model system that's going to help us to understand this is a nematode, a roundworm, called Caenorhabditis elegans. This worm comes in two different forms. So there are hermaphroditic, we call them females. They produce both eggs and sperm, and so these hermaphrodites can fertilize their own eggs with their own sperm. So this would be self-fertilization. And there are also males in the species that produce only sperm. So females can choose to either fertilize their own eggs or outcross with the males. And there are a few handy mutations that occur in these worms that make them a very, very good model system. There's a mutation that is lethal to males. So if we create an experimental population that fixes this mutation in the population, so we have a whole population with only hermaphroditic females, then we've got a whole population of individuals that are only self-fertilizing, they're only self-crossing. There's another mutation that renders the hermaphrodites unable to produce sperm, so they're turned into just regular females that only produce eggs. And then if you fix that in an experimental population, now you've got a population of obligate sexually reproducing individuals. This provides a really valuable experimental system that allows us to directly compare asexually reproducing, facultatively sexually reproducing, and obligately sexually reproducing populations of the same species. So this is going to be really useful to us in looking at these different mechanisms that seem to favor sexual reproduction. So first, let's look at one of these mechanisms in the abstract. And so this is our mutation drift model. And let's start out with the assumption that occasional mildly deleterious mutations are going to occur over time in any population. So let's think particularly about an asexually reproducing population. And so over time, you're going to have a distribution of individuals in that population with different numbers of deleterious mutations. Remember, the majority of mutations that occur are either neutral or mildly deleterious. The neutral ones are going to be subject only to genetic drift. These mildly deleterious mutations are going to be subject to mostly drift and very, very, very weak natural selection. So they can persist in the population because they don't have large fitness consequences. The numbers of individuals that have various numbers of these deleterious mutations are going to follow a normal distribution. So these are different mutations at different loci throughout the genome. We'll have a very small number of individuals with zero mutations, a relatively large with small number, because selection is working at some level against these deleterious mutations. There will also be a relatively smaller number with the largest number of deleterious mutations. So individuals with zero mutations in this case are more fit, but they're also quite rare. So they're going to be one of the rarest multilocus genotypes. Occasionally, genetic drift will remove the most fit genotype by chance. So all the random things that we've talked about that can cause the most fit genotype to be removed from the population, dumb luck basically, is going to cause that genotype to disappear from the population. So remember, this is an asexually reproducing population. There's no recombination. So once that multilocus genotype is gone, it is gone forever. So this causes the whole distribution to shift over to the right. So now the smallest number of deleterious mutations is 1, and we've got relatively more individuals with this larger number of deleterious mutations. And this process is going to continue, right? So now the most fit but rarest multilocus genotype is this 1 mutant category. Drift is eventually going to wipe that out by accident. And as this happens, with each elimination of the most fit and also most rare multilocus genotype, the average fitness of the population is going to decrease generation by generation as these deleterious mutations accumulate. So we see down here, now the smallest number of deleterious mutations is 2, and we're getting a less and less fit population. So this mechanism is known as Muller's ratchet. A ratchet is a mechanism that moves along incrementally and can't ever go backwards, right? It just keeps, with each turn, it goes one notch further. And so that's kind of analogous to the situation of once the most fit genotype is gone, it can never be brought back again in an asexually reproducing population. And now you've sort of turned the ratchet one step closer to this lower fitness in the population. And so we call this the accumulation of deleterious alleles in asexually reproducing populations. And this accumulation of deleterious alleles is also known as the genetic load. In sexually reproducing populations, that zero mutation multilocus genotype can be restored due to the recombination. It can always bring back those non-mutated versions of the alleles together, and you're constantly recreating this most fit zero mutation multilocus genotype. And so you don't get this ratcheting effect because these more fit multilocus genotypes can always be brought back by recombination, crossing over